So again, this is the amount of the pattern of our inductor current. This is the amount of our inductor voltage. This is the pattern or the response of our diode current, and this is the capacitor current. So on the voltage of our inductor, from the inductor point of view, during switch on, the whole V source is applied to the inductor. So the whole V source applied, so we have positive VL. Then during switch off, the inductor now become source which deliver current to the load and also to the capacitor. So the Vout, the output voltage VL now become the same element or the same parameter per what we measure at Vout, negative Vout. So VL equal to negative Vout actually, because this is negative by right. So it comes from here to the load. So this positive here, negative here by right. So this should be positive, negative. So we have here negative Vout. So negative Vout. Then start next cycle of positive VL, negative Vout, and so on. And from the diode point of view, here the diode, it happens that during positive cycle the diode is open circuit, so there is no current flows inside our diode. And during negative cycles, so there will be a maximum current per watt we measure here. So the maximum value here, and here are all the same. So IM max happen inside our diode, and it ran down to the IL minimum. And when the next cycle starts, so it reverse bias, no more current flows through, so it turns to 0. So start from the off time, the current flow to our diode, and stop during on time. Okay, what happened to the capacitor? You can see that when the current flow from our inductor here, so IL is equal to I which flow through C and plus the I that flow through our output. So IL equal to IC plus IOut. So if you want to find the IC, so IC is equal to IL minus IOut. So that's why we have here IL minus IOut. Means that it shifted, instead of what happened to in capacitor here, into the diode here, it shifted with the amount of IOut. Okay, shift down. So we have here IL max minus IOut, IL min minus IOut for the current that flow into our capacitor. Okay, IC equal to IL minus IOut. Okay, that's the how we can recognize, or we can draw our pattern of current and voltage output through our device here. And what happened to the output actually, on the output? Actually on the output point of view, in terms of voltage, Vout, and also in terms of IOut, and the output is a stable DC. But for buck boost, the output actually, we plot, it should be on the negative side. So it starts from 0, stabilize like that. So we can see that the output is on negative side. The analyze is taken during steady state, not during initial state here, but on the steady state and on the steady state. So that's the assumption that we made, that the analysis happen or being done during steady state condition. So for analysis point of view, so during on state, we have here VL equal to VS. VL equal to VS. Okay, it's equal also to the DL, DI, DT of our current. Okay, so when we perform the perbezaan, the differential equation on the equation, you can see that during the switch on period, the amount of the area below our curve here is equal to Vs dt divided by L. Okay, we shift the equation here into the amount of below the square. Here we can see that during on period, the delta IL that pass through our inductor is equal to V source times duty cycle times the period divided by L. Okay, during off state, you can see that the VL is equal to V out equal to L di dt. And we have here during off state, the amount of the area below the graph is equal to V out times the duration from dt up to the final times period divided by L. So both equation, delta IL and delta I up, and during on and off here, by right should be 0. For steady state operation, means that we are harnessing the circuit on the steady state condition. The inductor current must be 0. Same per what we have discussed or we assume on the buck and boost before. So the buck boost also we consider as a steady state, which is during on and off, the amount is 0. Plus on and off, 0. So solve for V0 or V out, we have V out equal to negative. This is the amount is negative because the buck boost we shall measure the output will be reverse. The parameter is the same, but in terms of polarity we shall see the reverse polarity. So negative Vs times dt divided by 1 minus d. So the required duty ratio can be expressed. We reshuffle the d, put in front. The duty ratio become parameter of V0 divided by Vs plus V0. So the output voltage we have opposite polarity for the source voltage, negative polarity lah. The output voltage magnitude can be less than the source or greater than the source, depending on the duty ratio of the switch. When we perform the analysis, if the duty cycle less than 0.5, we shall have a boost kind of scenario. If the duty cycle bigger than 0.5, it boosts up. Less than 0.5 will reduce. So if we have a 0.5, so we have a gain unity. Okay. Duty cycle is 1, so we have gain unity gain. Okay, this converter will combine the capabilities of the buck and boost converter because it can step up and step down based on the cycle that we manipulate. So note that the source is never connected directly to the load. So an LED is stored in the inductor and the switch. So it means that you can see that during switch on and off, so the source is not directly supplying the load, because when it switch on, it just supply the inductor, and during switch off, the inductor will supply the load. Okay. The buck boost converter is also called indirect converter. Means that the source will never connect to the load. It only will supply by the inductor and capacitor manipulation. The power absorbed by the load is the same as power supplied by the source. So we consider now as the losses in the inductor is not considered. Losses inside other components are not considered. So means all the power delivered by the source is transferred to the load. Okay, this analysis for the inductor current average inductor current. Okay, with the assumption that the output power is the amount of the delivered power, is that all the delivered power here consumed by the load. So we have here output power equal to V out square over R. So P equal to V square over R. This is the power equation. So same goes to the input. P source is equal to V source times I source. And when we equal both together, so V out divided by R is equal to V load or V inductor times I inductor, or V source times I source. So when the average source current is related, and the average source current is related to the average current by the inductor, which is I source is equal to IL D. So we put in inside this equation V out square divided by R equal to the source current, which is IL D times Vs. So we try to solve for average inductor current. Average inductor current. So IL equal to V out squared over R here times V source IL. So V source D times our V out squared divided by R. So it's equal to P out divided by V source times D. And we also know before that V out here is equal to negative Vs times D over 1 minus D. So Vs rearranged to become V out times 1 minus D divided by Vd. So we put in here the V source inside here. We solve for IL to be mentioned or formulated by V L divided by times D. Sorry, Vs times D divided by R 1 minus D squared. So we mention the load current in terms of source voltage times duty cycle times the resistor, the load value R times the involving duty cycle. So this is the average inductor current. So the Imax is obtained from the inductor average current plus the half of positive curve here. So we have IL max, and we have also IL min, which is I inductor average minus the half of the portion here. So delta IL divided by 2. So this is IL min, this is IL max. So for next analysis, so for continuous current, the inductor current must remain positive. CCM, the inductor current must remain positive. To determine the boundary between continuous and discontinuous mode, we can set the equation of minimum value of L min here to become 0. So L min here become 0. So we can get the amount of boundary, means that we set at 0, L min at 0, so we can get the minimum value of inductor value for boundary or between continuous and discontinuous mode. So take note that for the same frequency and load resistance, the buck converter has the highest minimum value inductor compared to the boost and buck boost. Boost converter have smallest L min, which result in wider range of inductor design. So the output voltage ripple, the delta V out compared by the average output voltage is equal to D divided by RCF. So the higher the frequency or the higher the amount here, we determine the best or the better voltage ripple for buck boost converter. So this is the parasitic element of DC converter. You can read through the conclusion